I want to do this really quick recording for you all to kind of remind you of some of your properties of logarithms. So the first one we want to talk about is if I take the natural log, or any log in particular, of a, let's say divided by b, this is equal to the natural log of a minus the natural log of b. A second property that will be useful is if I'm taking the natural log of a times b, this is equal to the natural log of a plus the natural log of b. And a third property that's often useful is if you're taking the natural log of, let's say, x to the power of r, that's r times the natural log of x. So the first property helps you break up the natural log of a quotient. The second property breaks up a natural log of a product. And then the third property helps you move exponents to the front when you have natural logs of something raised to a power. So how might that be useful? Well, you all are working on derivatives of composite functions, and I think I've assigned some where you might have something that looks like y is equal to the natural log of, let's say, x squared plus 2x divided by x plus 1. So if we were to do this normally, we would have to do the chain rule, and then you see there are some pieces here. So there's this first piece that's on the inside, and to take the derivative of that piece, that's going to require the quotient rule. And then we take the derivative of the outside piece, get another color here, which is a natural log. And then we put those two things together, we get our derivative. So that takes quite a bit of work. But if we take advantage of our properties above, we can simplify this drastically, and it reduces the work we need to do for our chain rule. So I could rewrite this by using the properties of logarithms. So it's y equals. Notice that in here, I'm actually taking the derivative of a quotient. So that's like a over b. So I can rewrite that as a natural log of x squared plus 2x. And then that'll be minus the natural log of x plus 1. All I've done here is this is just an algebra step where I've utilized those properties above, and in particular in this case I've used property 1. And so now I can take the derivative looking at the two pieces. This is part 1 there, part 2. Each of those will take a little chain rule. On the first part, see the inside function is x squared plus 2x. So I'm ready to start taking derivatives. So I'm going to write here that dy dx is equal to derivative of the inside of that first piece would be 2x plus 2, put parentheses around that. Then derivative of the outside is natural log, so remember that's always times 1 over whatever's on the inside, which is the x squared plus 2x. Now minus, put a big bracket because everything I do in there is going to have to get the minus sign. I just want to make sure I'm careful. Derivative of the inside, so derivative of x plus 1 is just 1. I'll put that there for emphasis. You don't really need it, but I just want you to see it. Then derivative of the outside function, natural log, that's times 1 over what was inside there, x plus 1. Okay, I can clean this up a little bit. So dy dx is equal to, I have a common 2, I'll pull that out. So that's 2 times x plus 1. That's all over the x squared plus 2x. And then minus, and then that's just 1 times 1. So that's minus 1 over x plus 1. And to make this so that it might fit perfectly into your WebAssign, and I'll leave that for you to do because it's just a little bit of arithmetic, but you may want to get a common denominator between this term here and here so that you get one fraction, because WebAssign is probably going to be looking for the most compact version of the answer. But this is a simplified way of doing something that otherwise would have taken you a bit more work having to do the quotient rule. And in fact, I'll go ahead and I'll kind of work through that for you. I won't simplify. So let's assume we hadn't done this. Put a line here. Let's change the color to orange, and let's say I did the quotient rule along with the chain rule. So I have to do the derivative of this inside portion. That's going to require that I do the quotient rule, so I write that out. Let's see, your top function, we're calling that f, so I'll call it f of x. So right here is x squared plus 2x. Bottom function is g of x. That's going to be x plus 1. Then I know I'm going to need f prime of x. Derivative of f of x is 2x plus 2, and then I also need g prime of x eventually, and that's going to be 1. And then I remember that the quotient rule is f prime g minus f g prime all over g squared. So the derivative of the inside, and I guess I'm about ready to start writing here, so my whole dy dx from that big function up there, to take the derivative inside, I'm going to need some brackets here. So it's going to be f prime g. So f prime is the 2x plus 2 times g, which is x plus 1, minus fg prime. So f is x squared plus 2x, and that's times g prime, which is 1, just putting that for emphasis, divided by g squared, which would be x plus 1 squared. So that is just the derivative, I'll scroll back up, of just this inside piece. Have to multiply by the derivative of the outside piece, and I'm going to do a carriage return so I have space, so that'll be multiplied times, and then just remember that the outside piece is a natural log, so it's just 1 over what's there. So it's 1 over, and then what's in there? X squared plus 2x over x plus 1. So that's x squared plus 2x over x plus 1. And then one cleanup I can do here is that when you're dividing like that, you invert and multiply. So I could rewrite this as dy dx is equal to, well, it'll be all this stuff here. So I'll just copy this, paste it in here. So it's all of that. And then it's going to get multiplied by this stuff here, just invert it. So that'll be times x plus 1 all over x squared plus 2x. And of course, there'd be some simplification to do in here, multiplying out, collecting terms. There might be things that factor, and then you'd have the bottom factors there. And so when you got done with your whole problem, it would look more something like, look like A over B, and that might be what they're looking for. But this is just an algebra step between here and what we got up here. We'd just take a little algebra. So I hope that helps. As I've shown you here, it'll be much easier if you go ahead and take advantage of these 3 properties. Go ahead and rewrite your functions when they have logarithms in there, and then come on down, take the derivative with much more straightforward chain rule problems.